We have one final topic to cover in the section on matrix inverses, and that's a refinement of the LU decomposition. So remember, the LU decomposition is that we write a matrix A is equal to L times U, where L is special lower triangular, which of course means that it's lower triangular, and special meaning it has ones on the diagonal, and U is upper triangular, meaning it's allowed to have anything on the diagonal, but it's required to be upper triangular. All right, what we're going to do next is a further decomposition. We're going to write this matrix U as D times V, where D is a diagonal matrix, and that means it has non-zero entries only on the diagonal. And V is special upper triangular. And you know what that means? It's just the analog of special lower triangular. Ones on the diagonal, zeros below, and anything above. Okay. And so the matrix U is this one here. It has A1 through AN down the diagonal. That's exactly what goes down the diagonal in D. And the star is supposed to indicate something above the diagonal. And this matrix V has something above the diagonal, but it's not necessarily the same something. So maybe it'd be better to write that with 2 stars. All right, so let's write that out again. So we have an upper triangular matrix, writing it as D times V. And let's just illustrate this with a 2 by 2 example. If you have an arbitrary upper triangular matrix, that's of the form A, B, 0, D. And I want to write that as a diagonal matrix. So that's a matrix that looks like this, times a special upper triangular matrix, which looks like that. Well, if you think about it, you'll see easily that the diagonal matrix has to be exactly this AD, as I mentioned here. This A and this D just become the A and the D over here in the diagonal matrix. And then let's just see what's left. When you multiply these, you get A plus 0 is A. And when you multiply these, you get just A. And we're supposed to get B. So if you think about it, what you do is you put B over A right here. So that's a formula for, if this is U, that's a formula for D and V, such that A is equal to D times V. And D and V were were handed to you. There's no other choice for those. And notice that for this to work, you certainly had to have A is not equal to 0. And so it's an easy proposition to see that if U is upper triangular, and the non-zero entries on the diagonal, then you can write U is equal to D times V. where D is simply the diagonal entries of U, and V is special upper triangular. And there's, as you can see from this example, V is not just the upper triangular entries of U. It's got this B over A here. And if you look at this equation here, you can see what is V? Well, we could multiply both sides of this equation by D inverse to get that D inverse U is equal to V. And I've already told you what D is. It's just the diagonal entries A1 through AN. U is what you're handed, so you just do this multiplication. It's easy to compute D inverse, of course. D inverse will just be A1 inverse dot 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 AN inverse down the diagonal. And so that gives you a formula for V. Okay, so putting that together, we arrive at the following. If we write a matrix A is equal to LDV, that's called, surprisingly enough, the LDV decomposition of A, where I won't write it down, but L is special lower triangular, D is diagonal, and V is special upper triangular. And just as we had the permuted LU decomposition, there's also the permuted PLDV decomposition, PLDV, or that's sometimes written putting the P on the other side, PA is equal to LDV. Either one of these is sometimes called permuted LDV decomposition. And what matrices have such a decomposition? So it's a basic fact that if A is non-singular, that implies it has a permuted PLDV decomposition. And if A is regular, that means it has an LDV decomposition. But I don't like this statement because it doesn't really mean anything, because what is regular? If you look in the book, regular is all of the matrices which have an LU decomposition. So this theorem isn't saying anything, or this statement isn't saying anything except perhaps the definition of regular. So I wouldn't put too much stock in that. In some sense, the more important result is this one about the permuted PLDV decomposition. Now, I'll do an example in a minute, but I want to state one last thing first, which is about uniqueness. And this is a little tricky, but it's an important result, so let me state it. Theorem, if A has an LU decomposition, then it's unique. LU are unique. Whoops, are unique. That is to say, if you write A is equal to LU, or if you write it in as L prime U prime, where both L and L prime, of course, are special lower triangular, and both U and U prime are upper triangular. If you write it in such a way, then the only way that this can be done is because L is equal to L prime and U is equal to U prime. So that's an important fact. The LU decomposition, when it exists, is unique. Well, so let me indicate why this uniqueness holds. This is a basic kind of idea that comes up a lot. So proof of uniqueness of the LU decomposition. Suppose I had a matrix A and I wrote it as LU, but I also wrote it as L prime U prime, where, as I mentioned, L and L prime are special lower triangular, and U and U prime are just ordinary upper triangular. Well, if you take this equation and you bring the L prime to the left-hand side and the U to the right-hand side by taking inverses, what you get is that, well, what do I do here? I multiply both sides of this equation by L prime inverse, and here I multiply both sides of this equation by U inverse. What I get is that the matrix L prime inverse times L, that's the left-hand side, is equal to U prime times U inverse. Okay, so maybe I'll write this as a slanty prime to make it clear that's a prime. Okay, and if you look at this equation, well, let's look at the left-hand side. The left-hand side, this matrix is special lower triangular, and the inverse of a matrix of such a matrix is still special lower triangular, and this matrix is special lower triangular. So this whole side is the product of two special lower triangular matrices, which is therefore special lower triangular. On the other hand, this side is the product of an upper triangular matrix and the inverse of an upper triangular matrix. Well, the inverse of an upper triangular matrix is still upper triangular, so, and the product of two such matrices is upper triangular, so this side is upper triangular. Okay, well, so what do we have? We have two matrices that are equal. One of them is special lower triangular, that is to say, it has ones on the diagonal and looks like this. On the other hand, it's equal to a matrix which looks like this. Well, how can this matrix equal this matrix? The only way is if both of those matrices are 1. Ones on the diagonal, zeros below and above. Ones on the diagonal, zeros below and above. You have to have zeros below because of this. You have to have zeros above because of this. And you have to have ones on the diagonal because of this. So both of these matrices are equal to the identity. And that says that L is equal to L prime. And U is equal to U prime. Okay, so what I just proved is that this decomposition, if I write a matrix A as equal to L times U, that L and U are unique. And similarly, if I write a matrix U is equal to D times V, then D and V are unique. And it's essentially the same arguments. And so therefore I conclude, I'll state this as a theorem, I'll restate what I just had, which is that the LU decomposition is unique, and the LDV decomposition is unique. All right. And again, what do I mean by that? If you take a matrix A and write it as a product of special lower triangular, diagonal, special upper triangular, there's only one way to do that. And you might be tempted to think the same thing holds true of the permuted LDV decomposition, but that's not true. So I'm going to write here A equals P LDV is not unique. And I'll leave it to you. Maybe you should pause the video now and find an example of a matrix A, which can be written as in a permuted PLDV decomposition in more than one way. Okay, that's all I have to say about the LU and LDV decomposition for general matrices. The next thing is a brief section on symmetric matrices, which are of particular importance. So let's recall that if A is an m by n matrix, then the transpose of A which is written A upper T, is an n by m matrix. And the way we obtain it is we switch the rows and the columns. And another way to say it is you flip the matrix around the diagonal. So, for example, if you have the matrix A, B, C, D, E, F, its transpose is a 3 by 2 matrix whose first column is ABC and whose second column is DEF. And of particular importance, of course, is square matrices ABCD. Transpose is ABCD. And we say a square matrix, an n by n matrix, A is symmetric if it's equal to its transpose. A is equal to A transpose. Okay, so for example, what are all of the 1 by 1 symmetric matrices? Well, a 1 by 1 matrix is just a number, and that's always equal to its transpose. What about 2 by 2? What are the 2 by 2 symmetric matrices? Well, let's see. So a 2 by 2 symmetric matrix has to look like this, and its transpose looks like this. And I'd like to know if these two things are equal to each other. Well, A is certainly equal to A, and D is certainly equal to D, but I'd better make sure that B is equal to C, and I also better make sure that B is equal to C. Well, that's redundant, so a 2 by 2 matrix is symmetric if and only if it's of the form A, B, B, A. Excuse me, A, B, B, D. And similarly, here are all of the 3 by 3 symmetric matrices. A, B, C, D, E, F. Can have anything upper triangular, and then the stuff below the diagonal has to come from above the diagonal. Okay, now the main thing we're going to talk about here is the LDV decomposition of a symmetric matrix. So suppose A is symmetric. And suppose it has an LDV decomposition. So again, that's what the book calls regular. To say it has an LDV decomposition, it says that A is equal to LDV, where, as always, L is special lower triangular, V is special upper triangular, and D is diagonal. Now, a basic property of the transpose is that if you take two matrices and multiply them and take their transpose, that's the product of the transposes, but in the reverse order. So when you take the transpose of a product, you reverse the order, and that holds for any number of terms. So that says that if you take this identity for A and take its transpose, you conclude that A transpose is LDV transpose. And by the comment I just made, that's the same as the transposes in the reverse order, V transpose D transpose L transpose. Okay? And we're assuming that A is symmetric. So let's write this is equal to A. And this is because I've assumed A is symmetric. So I have two different expressions, very similar expressions for A. I've written it as LDV, and I've also written it as V transpose D transpose L transpose. Now, what do we know about these matrices? L, for example, is special. I'll drop the word special, is lower triangular. What do you know about V transpose? Well, V is upper triangular. So when you take its transpose, the transpose of an upper triangular is lower triangular. So this matrix V is lower triangular, just like L, and it's also special. It has ones on the diagonal. Okay, so let's write that again. We have two decompositions now. We have written A as LDV, but from the calculation I just did, I also have that A is equal to V transpose D transpose times L transpose. This is assuming that A is symmetric. And, excuse me, what do we know about D transpose? Well, if you take the transpose of a diagonal matrix, it's just itself. So we can write this as V transpose D times L transpose. And look what we've done. V was special upper triangular, so V transpose is special lower triangular. D is diagonal, and L transpose is special what? L is lower triangular, so L transpose is upper triangular. And that's the same property that these matrices have up here. Excuse me. Up here. Special lower triangular, diagonal, special upper triangular. And remember, we have uniqueness of the LDV decomposition. And so by uniqueness, I conclude that these matrices must be the same, L and V transpose. And, well, of course, D is equal to D, and also V is equal to L transpose. But that's just the same fact again. But what I conclude is that, I'll write it this way, V is equal to L transpose. That's this identity right here. And I've concluded that if A is symmetric, and it has an LDV decomposition, then the LDV decomposition, in fact, is a special one. In fact, you conclude that A is equal to LDL transpose. So this is a special form of the LDV decomposition for a symmetric matrix. The bottom line is that you only have to compute, in essence, half as much information. If you take a typical matrix and you want to compute its LDV decomposition, you have to compute the diagonal matrix and 2 triangular matrices. Let me write a new one over here. Oops. So in general, if you have an ordinary matrix and you want to compute its LDV decomposition, you have to compute 2 triangular matrices. But if A is symmetric, then you only have to compute one of those matrices and use the transpose for the other. Okay, so let's illustrate the procedure for finding the, I want to write this as L, D, L transpose. This is the LDL transpose decomposition of this symmetric matrix. So how do you do this? Well, the first thing that you do is just the old-fashioned find A is equal to LU. That's part of the way there. And you do this by the Gaussian elimination process. And maybe I'll pause here and let you do that on your own. So why don't you compute the LU decomposition of this matrix, and when you're done, start the video again and see what you get. Okay, let's see. What I got was A is equal to the special lower triangular matrix 1, 1, 1, 2, 1, minus 1. Times 1 minus 2, 4 down the diagonal. And 2, 1, 2 above the diagonal. Okay. So what do you do now? So this is my L, and this is my U. And the cool thing about symmetric matrices is that you're done. You don't have to do any more work. The point is that you already know L transpose, because you already know L, and you already know D, because D is simply the diagonal matrix, the diagonal matrices of this matrix right here. So we've just done the entire computation. We find that A is equal to 1, 1, 1, 2, 1, minus 1, times the diagonal entries here, 1, minus 2, 4, 0, 0, 0, 0, 0, 0, times the transpose of L, which is to say 1, 1, 1, 2, 1, minus 1, 0, 0, 0. So that's the thing to keep in mind when you're doing the this decomposition of a symmetric matrix. You could have done a lot more work to finish this computation. If you weren't smart, you would have done some more Gaussian elimination on this matrix to compute dV, or DL-transpose, and so on, but that's not necessary. This is your L, D, and L-transpose matrices, and I'll leave it to you to check that this equation really is correct.